In 1962, a single unexpected signal from space nearly convinced NASA that their most expensive satellite was dead. But it wasn't broken, it was being attacked. The real culprit wasn't a design flaw or a launch failure. It was something no engineer had fully accounted for: invisible particles streaming from the sun, colliding with Earth's upper atmosphere, and firing straight through the electronics that were supposed to keep our satellites alive. And for nearly a decade, nobody understood why. To understand how close we came to losing the satellite age before it even started, you need to step back to the late 1950s. The space race wasn't just about prestige, it was about survival. The Soviet Union had launched Sputnik. The United States was scrambling to prove it could do more than follow. By 1960, NASA had committed enormous resources to Telstar, a communications satellite that would relay live television signals across the Atlantic. It cost $60 million, equivalent to roughly $600 million today. It was a bet the farm moment. Everything about it had to work perfectly, because if it didn't, the entire program was in jeopardy. The satellite launched in July 1962. For weeks, it performed flawlessly. Engineers watched telemetry data stream back from orbit. The signal was clean. The relay worked. Television images bounced from Maine to France without degradation. This was going to change the world. Then, abruptly, the data started corrupting. Telemetry readings that should have been stable began to drift. Signal errors appeared where there should have been none. Engineers pulled up the raw numbers and felt their stomachs tighten. Something inside the satellite was failing. The problem was intermittent. The satellite would work perfectly, then glitch, then recover. It was erratic in a way that made no engineering sense. You could predict a mechanical failure, worn bearings, a fractured wire, a dead battery, but this was something else entirely. The team started investigating every possibility. They checked the power systems, they reviewed the circuit boards, they traced every wire and connection looking for a short or a crack. Nothing. The hardware was sound, the design was solid, yet the failures kept happening. Then one engineer noticed something buried in the data. The errors spiked during solar activity. When the sun was quiet, Telstar worked flawlessly. When solar radiation increased, the glitches multiplied. It was a correlation that seemed impossible. The sun was 93 million miles away. How could it possibly affect a satellite's electronics? The answer lay in cosmic rays, high-energy particles born in supernova and accelerated across the galaxy at nearly the speed of light. When the sun's magnetic field became active during solar storms, it actually blocked some of these particles. When solar activity was low, cosmic rays rained down on Earth unimpeded. But here's what made this dangerous. When a cosmic ray struck a semiconductor in Telstar's electronics, it could flip a bit, a single zero becoming a 1 or vice versa. Just one bit, one particle, and suddenly a perfectly valid instruction became corrupted. The satellite would misinterpret commands or produce bad data. This phenomenon, cosmic ray-induced bit flips, wasn't theoretical. It was happening in real time, in real orbit, to a satellite worth $500 million, and no one had designed Telstar to withstand it. The engineers had been so focused on mechanical reliability that they'd overlooked the invisible threat from space. The implications were staggering. If cosmic rays could corrupt Telstar, they could corrupt any satellite. Every computer in orbit faced the same vulnerability. The entire communications infrastructure that the world was about to build could be undermined by particles from distant explosions billions of years old. But the discovery also forced a reckoning. Engineers couldn't shield satellites completely. The weight and cost would be prohibitive. Instead, they had to think differently. They implemented error detection codes that could identify when a bit had been flipped. They added redundancy, backup systems that could take over if the primary failed. They also learned to predict cosmic ray impacts based on solar activity. By monitoring the sun, they could anticipate when their satellites were most vulnerable and schedule critical operations during quiet periods. Space weather became as important to mission planning as rocket fuel. The cosmic ray crisis of the early 1960s became the hidden foundation of modern satellite design. Every GPS receiver in your pocket, every weather satellite, every communications relay in orbit, they all exist because engineers learned to account for an invisible threat that almost derailed the entire enterprise. Telstar itself survived. Engineers adjusted its operation, accepted the occasional glitch, and kept it transmitting. It operated until 1963, when solar activity actually damaged it beyond recovery. But by then, the lessons were learned. The next generation of satellites was built to withstand what the cosmos could throw at them. So when you use your phone to check the weather or watch a live broadcast beamed from across the world, you're relying on technology that was hardened in the crucible of a crisis most people have never heard of. The cosmic rays didn't break the satellite age, they built it. Subscribe to uncover the hidden crises that shaped the space age, the ones engineers had to solve before anyone even knew the problem existed.